Thanks for being in my presentation today. I hope everyone is doing well. I'm Wang and currently a research associate from Satellite Navigation and Sensing Lab at the University of Colorado Boulder. Today, I'm going to give a talk about a carrier phase tracking architecture for positioning in LTE networks under channel fading conditions. I will start with a background about cellular localization techniques, followed by the LTE signal model. Then I will elaborate the closed-loop carrier tracking method for LTE signals and provide both simulation results and experimental validation for the proposed method. Finally, I will give a brief summary. Talking about cellular localization, there are two categories of techniques in general. Standalone technique means that localization is achieved solely relying on cellular networks. Such techniques include cell ID method. An easy explanation is to consider the position of the solving cell that the user is connected at the user location. Intuitively, this method is very simple, but only provides limited accuracy. Fingerprinting technique is popular for indoor areas, which explores a predetermined database of received cellular signal characteristics. The difficulty lies in the establishment and update of this database for a wide coverage area. Time of arrival technique is essentially a type of trilateration method, similar to GNSS. The insufficient number of measurements and severe multipath effects are the major threats to the accuracy of this technique. The second category is a hybrid technique, which integrates the ranging measurements from multiple systems. For examples, the integrated GNSS cellular and INS cellular positioning have received substantial attention within the navigation community. Among these techniques, those using TOA measurements from cellular systems all require the signal processing of cellular signals. Here, let's focus on the current 4G LTE cellular networks. As I just mentioned, the LTE signal processing is vulnerable to the multipath propagation effect, which is very common in urban areas. Both reflected and scattered signals would contaminate the left-side signal. Because of the user mobility, the propagation channel can generally be characterized by a multipath feeding channel. Here I show two channel examples. One is a simulated frequency-flat Rayson feeding channel, also meaning a single pass condition. This path gain fluctuates significantly and shows up to 10 dB degradation for a couple of short time periods. The second example is a multipath feeding channel from real data, which I will explain in more details later. The three paths in this channel show time-varying gains. It's also worth noting that the channel dynamics in this real dataset are much lower than that in the simulation, mainly due to our slowly moving data collection platform. These multipath fading effects can cause trouble in LTE signal processing, including both TOA estimation and carrier synchronization. We had a presentation in last year's conference talking about the TOA estimators for LTE signals under multipath conditions. You may refer to the paper listed at the bottom if you are interested. And this talk is about the LTE carrier synchronization. At first, I would like to talk a little bit about the LTE signal model. Here is a schematic of how to generate the LTE signal as a transmitter and obtain the baseband signal as a receiver. As a transmitter, a core step is to convert the frequency domain transmitted symbols to a time domain sequence through an inverse discrete Fourier transform along with cyclic preface addition. Considering both the multipath propagation channel and thermal noise, the received signal model is shown at the bottom. The first exponential function underlined in blue is due to the non-ideal carrier synchronization. The portion underlined in green represents the multipath effects. We next introduce our proposed closed-loop carrier tracking method. We use a two-state vector X to donate the LTE signal carrier state, as in general, LTE signals have low dynamics compared to GNSS signals, considering the fixed position of the cellular tower. The received baseband signal is first multiplied by the local carrier replica for carrier wipe-off. Then, based on the symbol timing estimation, the samples pertaining to each OFDM symbol are extracted. This sample set goes through a flow opposite to the signal generation. The CP is first removed, and the remaining useful part is converted to frequency domain through a DFT operator. The demodulated frequency domain samples are multiplied by the conjugate pelotons and compensated by the timing error estimation to generate the channel frequency response estimation H hat. Here the pelotons are referred to as the cell-specific reference signal. The CRS transmission pattern within one slot is shown as rightmost. It is only transmitted in the first and fifth symbols within each slot, and the subcarrier spacing between two CRS pelotons are 6. Then, the CFR estimations over multiple slots within an updating interval can be integrated as the input to the phase discriminator. The carrier phase error is then measured and filtered by a low-pass filter for updating the carrier state. Here is only the block diagram of the tracking method, and I will explain the discriminator and filter modules with more math in the next few slides. Here I directly show the equation for the CFR estimation. The detailed derivation can be found in our full paper. The CFR estimation equals to the multiplication between the exponential function of the average phase error and the true CFR, except for the noise term. Thus, the carrier phase error can be measured as the phase information in the summation of the CFR estimations at all subcarriers transmitting the CRS. In the previous slide, I mentioned that the CRS is only transmitted in the first and fifth symbols within each slot. This slide shows the expressions for two cases, one using only a single symbol, and the other using the first symbols within all slots for an updating interval. And the results in additive wide Gaussian noise channel are also provided. We can see that the measured carrier phase error depends on the used symbol indices, which implies different phase averaging time. But for multipath channels, due to the involvement of all the multipath signals, there would be a bias in the discriminator output. In this slide, the analytical expression of the multipath-induced carrier phase error is provided in the yellow shaded frame. This error depends on not only the multipath parameters, but also the signal bandwidth. We use the common metric multipath error envelope to quantitatively evaluate the carrier phase error and show it on the right. We assume a noise-free condition and a two-path channel. We then calculate the maximum and minimal biases in the carrier phase discriminator output for a specific multipath delay. The top panel shows the results for a fixed signal bandwidth and different multipath to direct signal power ratios. In the bottom panel, we fix the MDR and vary the signal bandwidth. We can see that the carrier phase error exhibits a fluctuating characteristics with respect to the multipath delay, and a stronger multipath signal or a smaller signal bandwidth leads to a larger carrier phase error for the same multipath delay. We also would like to point out that multipath error analysis for LTE signals have similarities but also differences relative to GNSS signals. We then present the loop filter design in this method. In fact, we borrowed an idea from the advanced GNSS receiver carrier tracking design and optimization proposed by one of my previous colleagues and adapted it for LTE signals. The relevant reference is provided at the bottom. In the system model, one thing that I would like to point out is that the phase averaging time is not equal to the loop updating interval, since the CRS is not transmitted at all symbols. Based on the established system model, we apply the control system design technique to derive the state estimation gain matrix by comparing the transfer function with the conventional proportional integral filter. The benefits of this loop filter design would be the convenience for tracking performance evaluation under various operating conditions and the development of adaptive tracking algorithms in challenging conditions. These are left for future work. First, we would like to present some simulation results. In the simulations, we assume a frequency flat Rayson fading channel so that we can focus on the effects of path fading on the carrier phase tracking. Other signal parameters and tracking loop parameters are provided in the two tables on the left. In fact, we did a thorough performance assessment using different loop parameters for various signal conditions, and we'll show them in the subsequent slides. We thus ensure that the loop parameters shown in this table are appropriate for this signal condition. The top figure shows the instantaneous path gain, indicating several deep amplitude fading. The middle figure provides the detrended results of the true and estimated carrier phases. A linear trend in the carrier phase due to the constant Doppler frequency is removed. The estimated and true values are in good agreement. This detrended phase also indicates the path phase fluctuation in the fading channel. It clearly shows that the fast phase changes correspond to deep amplitude fading. The bottom figure gives the carrier phase estimation error, which demonstrates the carrier phase tracking capability of the developed method under channel fading conditions. The maximum magnitude of the estimation error is about 0.06 cycles at around 0.0 seconds with the deepest amplitude fading. Then we implemented three channel realizations with different key factors and obtained the carrier phase estimation accuracy for different SNR, key factor, and updating interval. Note that a higher key factor means lower channel dynamics. For each condition, we run 100 Monte Carlo simulations and calculate the average value of the root mean square errors for all simulations. It is verified that the proposed method can achieve high accuracy carrier phase estimation under strong channel fading conditions. Moreover, the accuracy improvement contributed by increasing the updating interval is more noticeable for smaller key factors. This figure shows the estimation accuracy versus loop bandwidth in two specific scenarios: a noise dominant scenario with a high key factor and a low SNR, and a dynamics dominant scenario with a low key factor and a high SNR. For the noise dominant scenario, the major contributing factor of the carrier phase error is thermal noise. Therefore, a smaller loop bandwidth is beneficial for obtaining a smaller root mean square error. Where channel dynamic error is the dominant component in the carrier phase error for the dynamics dominant scenario, the root mean square error decreases with the increasing loop bandwidth. These results indicate that the loop bandwidth should be set considering both signal power and channel dynamics. We next show the experimental results from a real dataset. The left picture is an environmental picture of the data collection experiment conducted on this January at Singapore. The data collection platform at a fairly low speed is surrounded by a number of tall buildings, indicating urban environment. The right plot gives the schematic of the experimental setup for the data collection system. The LTE signals are fed into an USRP software-defined radio at a bandwidth of 25 MHz and 16-bit samples. We implemented three tracking schemes for processing this real dataset. The first one is open-loop carrier tracking in conjunction with the Esprit, which is known as a high-resolution TOA estimator. The second one is a closed-loop carrier tracking with a conventional delay log loop to track the TOA. And the third one is a closed-loop carrier tracking with the multipath estimating delay log loop, which was also an idea we borrowed from GNSS multipath mitigation technique and applied to LTE signal TOA estimation. The results have been recently published in this IEEE journal paper. Here I won't go into details about all the TOA estimation methods. If you are interested, please check this paper. Let's first see the multipath channel characteristics in this dataset provided by the MEDLL. The left figure is the path TOA and the right figure is the path gain. We can see that there are three predominant paths with path delay of about 40 and 60 meters relative to the first arriving path. In the first 4 seconds, path 0 has the strongest power among the three paths, which is an indication of a left side condition. Starting from around 4 seconds, path 0 is more attenuated than the later arriving two paths. Therefore, the last 6 seconds can be regarded as a harsh multipath condition. The four plots in this slide are ranging measurements we obtained from a 10-second real dataset. The left two are the TOA estimations using 0.5 and 1 millisecond updating intervals, and the right two are the carrier phase measurements for two updating intervals. Each plot shows the results provided by three methods. We can see that the TOA estimation and the carrier phase measurement show a good agreement in the variation value over the 10 seconds period. The TOA estimation is much noisier than the carrier phase measurement. The Esprit without application of a loop filter suffers from numerous large biases in the TOA estimations, When compared to the other two closed-loop methods, the number of large biases is effectively reduced by increasing the update interval to 1 millisecond. The TO estimations provided by the DLL deviate from those obtained from the Esprit and MEDLL, especially for the last 2 seconds due to the harsh multipath conditions. To exhibit more details in the carrier phase measurements, we show the detrended carrier phase values here. For detrending, the same linear carrier phase trend extracted from the closed-loop MEDL results is subtracted from the carrier phase estimations provided by the three schemes. We can see that the open-loop results show a larger estimation variance compared to the other two closed-loop results. It is also worth noting that the remaining dynamics in the detrended carrier phase may originate from the clock dynamics and platform motion. In addition, there are actually certain biases between the closed-loop DLL and closed-loop MEDL results. This bias will be better displayed in the next slide. For a comparative analysis of the considered schemes, we calculate the difference of the carrier phase measurements between two methods for 1 millisecond updating interval. Thus, we remove the common components, such as clock dynamics and platform motion, and the multipath effect and noise remain as the contributing factors in the phase difference. The phase difference between the open-loop Esprit and closed-loop MEDL exhibits noise-like characteristics. To verify this, we plot the histogram of this phase difference on the right. The PDF is pretty close to a normal distribution with an almost zero mean and a standard deviation of around 0.01 cycles. In general, the multipath-induced errors should be low-frequency components and uncorrelated in the two methods. Results may infer that the phase difference is dominated by the estimation noises. That is to say, the open-loop Esprit and closed-loop MEDL both show success in mitigating the multipath effects on carrier phase estimation. However, the phase difference between the closed-loop DLL and closed-loop MEDL in the subplot B constantly incorporates a non-zero bias. This bias should mainly come from the multipath-induced error in the closed-loop DLL. The bias is around minus 0.1 cycles for the last 0.5 seconds when pass 0 becomes about 8 dB weaker than pass 1. Lastly, I would like to give a brief summary of this talk. We adapted our previous GNSS receiver state space carrier tracking method to LTE signals for positioning applications. We analytically derived the multipath-induced error in the conventional carrier phase discriminator. We evaluated the carrier phase estimation accuracy through simulations for various signal and channel conditions. And we also presented an experimental validation of the developed carrier tracking method in a multipath feeding channel using real collected LTE data. We would like to thank our funding providers for supporting this project and our colleagues and collaborators for conducting the experiment. Thank you very much for your attention. We provided our email addresses here, and please email us if you have any questions or comments.